The Messerschmitt Me 262 marked a revolutionary moment in aviation history as the world's first operational jet-powered fighter aircraft. This groundbreaking machine reached speeds of up to 540 mph, outpacing the fastest Allied piston-engine fighters by more than 100 mph. The engineering behind the Me 262 represented numerous technological breakthroughs. Its twin Jumo 004 turbojet engines delivered unprecedented thrust, while its swept-wing design and armament system, featuring four 30mm cannons, demonstrated remarkable innovation. The aircraft's development demanded solutions to complex challenges in metallurgy, aerodynamics, and control systems. This video will examine the extraordinary engineering achievements that made the Me 262 possible, from its revolutionary propulsion system to its advanced weapons integration. You will discover how German engineers overcame significant technical obstacles to create an aircraft that would influence fighter design for decades to come. Revolutionary propulsion system. At the heart of the Me 262's groundbreaking capabilities lay its Junkers Jumo 004 engine, the world's first production turbojet engine to enter operational service. This pioneering power plant featured an 8-stage axial flow compressor, 6 straight-through combustion chambers, and a single-stage turbine. The development of the Jumo 004 engine commenced in 1937, marking a significant milestone in aviation engineering. By the time it reached its final production configuration, the engine was capable of producing an impressive 1,980 pounds of thrust, a feat that underscored its advanced design and engineering sophistication. Central to the Jumo 004's performance was its innovative architecture, which integrated several groundbreaking features. At the heart of the engine was an 8-stage axial flow compressor that achieved an efficiency of 78%, a remarkable achievement for its time. This efficient compression system was complemented by 6 straight-through combustion chambers, which optimized the fuel-air mixture for combustion. Further enhancing its performance, the engine utilized a single-stage turbine equipped with hollow blades, a design choice that balanced strength and weight while ensuring effective heat dissipation. Additionally, the Jumo 004 incorporated a variable geometry nozzle system, which allowed for dynamic adjustment of exhaust flow, improving efficiency and thrust under varying operating conditions. Another notable aspect of the Jumo 004 was its exceptional adaptability in terms of fuel. The engine was capable of running on a wide range of fuels, including J2 synthetic fuel derived from coal, diesel oil, and conventional aviation gasoline. This versatility in fuel compatibility made the Jumo 04 a practical and resourceful choice for its era, especially during wartime conditions when fuel availability was often constrained. Overall, the Jumo 004 stood as a testament to the ingenuity and forward-thinking approach of its designers, influencing the trajectory of jet engine development for years to come. Material constraints posed significant hurdles in the engine's development. Germany's limited access to critical metals necessitated innovative solutions. The shortage of essential materials like chromium, nickel, and cobalt forced engineers to redesign the 004 billion engine using alternative materials. The production version utilized mild steel for high-heat components protected by aluminum coating. This compromise significantly impacted engine longevity. Production engines required overhaul after just 10 hours of operation and complete replacement after 25 hours. The Jumo 004 incorporated advanced thrust control systems, featuring a variable geometry nozzle design. This plug nozzle system moved approximately 40 centimeters fore and aft, utilizing an electric motor-powered rack and pinion mechanism to adjust the exhaust cross-sectional area. However, the engine exhibited characteristic early jet engine challenges, particularly in throttle response. Rapid throttle movements could lead to excess fuel injection into the combustion chambers, resulting in dangerous temperature spikes before airflow could compensate. Engineers addressed this through careful governor design and operational protocols. The engine's production process was remarkably efficient, requiring only 375 hours for manufacture, assembly, and shipping, a significant improvement over contemporary piston engines that needed 1,400 hours. Despite its limitations, the Jumo 004 represented a crucial milestone in jet engine development, establishing foundational principles for future jet propulsion systems. Aerodynamic breakthroughs. The aerodynamic design of the Me 262 represented a significant leap forward in aircraft engineering, particularly in its innovative wing configuration. The aircraft's distinctive swept wing design emerged from practical necessity rather than theoretical planning. The Me 262's wing design underwent significant evolution during development. Initially conceived with straight wings, engineers had to adapt when the engines proved heavier than anticipated. The solution was an 18.5° sweep angle for the outer wing panels. This adjustment, while primarily intended to address the center of gravity issues, inadvertently provided enhanced performance at high speeds. The wing construction featured single spar cantilever design with stress skin, root thickness of 3 mm tapering to 1 mm at wing tips, modified NACA airfoils with elliptical nose sections, and unfinished wing interiors to reduce weight. Ludwig Bolko, the chief aerodynamicist, implemented sophisticated airfoil designs to optimize airflow. The wing utilized different NACA profiles. The NA011-0.825-35 at the root and NACA 0009-1.1-40 at the tip. This combination provided optimal lift distribution while managing the challenging aerodynamic forces at high speeds. The Me 262's aerodynamic design delivered exceptional performance metrics. The aircraft achieved a maximum speed of 540 mph and could climb at 3,937 feet per minute. This represented a significant advantage over Allied fighters, such as the P-51 Mustang, which topped out at 437 mph. However, the design had its limitations. The aircraft encountered severe controllability issues as it approached Mach 0.86, though it maintained effective performance up to its tactical Mach number of 0.82. These high-speed characteristics demanded new combat tactics, particularly when engaging enemy aircraft. The aircraft's ceiling of 38,000 feet allowed for tactical advantages, especially in intercepting Allied bomber formations. Pilots developed specific attack patterns, including the roller coaster approach, initiating engagement from 1,800 meters above their targets. This tactical adaptation maximized the aerodynamic advantages while minimizing exposure to defensive fire. The Me 262's aerodynamic configuration proved so successful that it influenced post-war aircraft design significantly. Its swept wing layout and twin-pod engine arrangement became standard features in subsequent fighter aircraft and commercial airliners. Materials engineering. Material constraints posed one of the most significant challenges in the development of the Messerschmitt Me 262, forcing German engineers to implement innovative solutions throughout the aircraft's construction. The challenges posed by the scarcity of essential metals during wartime compelled engineers to adopt innovative and resourceful approaches to materials science and design. Germany's limited access to crucial materials such as nickel, cobalt, and chromium created significant obstacles for manufacturing, particularly in the production of advanced military technologies. To overcome these limitations, engineers were forced to devise alternative solutions, resulting in notable modifications to conventional design practices. One of the most prominent adaptations involved the substitution of materials to conserve scarce resources. Aluminum-coated steel was employed as a replacement for nickel-based alloys, which were traditionally favored for their durability and resistance to high temperatures. This substitution provided a workable compromise, offering sufficient performance while reducing dependence on materials in short supply. Similarly, modified steel alloys were developed and incorporated into various engine components, balancing the need for strength and heat resistance with the availability of substitute materials. Efforts to minimize the use of strategic metals extended beyond engine components to the structural elements of aircraft and other military equipment. Engineers deliberately reduced the quantities of high-value metals in structural designs, opting for more abundant or easily obtainable materials wherever possible. This resource-conscious approach also influenced broader construction choices, such as leaving wing interiors unfinished to conserve both materials and manufacturing effort. These creative adaptations not only addressed the immediate challenges of material shortages, but also showcased the ingenuity of wartime engineering. The resulting designs reflected a delicate balance between performance demands and resource constraints, illustrating how necessity can drive innovation in even the most challenging circumstances. The substitution of materials created substantial challenges in managing the extreme temperatures generated by jet operation. The production version of the Jumo 004 billion N utilized aluminum-coated steel for high-temperature components, a compromise that significantly impacted performance. This solution, while allowing for mass production, reduced engine reliability to just 10 to 25 hours of operation. Engineers developed specialized coating techniques to address heat-related issues. They implemented an aluminum flame spray coating process for critical components, representing an early application of thermal barrier technology in jet engines. To maintain structural strength while working with alternative materials, engineers implemented several innovative design solutions. The wing construction featured varying thicknesses, from 3 mm at the root to 1 mm at the tip, optimizing weight distribution and structural integrity. This approach allowed for effective load management while minimizing the use of scarce materials. The aircraft's construction incorporated single spar cantilever wings with stress skins, a design choice that balanced structural requirements with material availability. To further conserve strategic materials, late-war production models featured unpainted wing interiors, a modification that reduced weight while preserving structural integrity. The material constraints led to a continuous process of engineering adaptation. While German expertise in metallurgy was substantial, the shortage of critical metals remained a persistent challenge. Engineers responded by developing improved coating technologies and exploring alternative material combinations to extend component lifespans. These material engineering solutions, while not ideal, demonstrated remarkable ingenuity in overcoming severe resource limitations. The techniques developed for the Me 262 contributed significantly to understanding the behavior of alternative materials in high-stress aviation applications. Control systems engineering. The engineering of the Me 262's control systems represented a sophisticated blend of mechanical precision and pilot-centric design. The aircraft's control architecture integrated multiple innovative features that enabled precise maneuvering despite its unprecedented speed capabilities. The Me 262's primary flight controls centered around a sophisticated ball and socket-mounted control stick system. The stick assembly extended 4 inches downward from the cockpit liner, terminating in a welded angle bracket. This design connected to a complex network of push-pull tubes and bell cranks that translated pilot inputs into aileron movements. The elevator control system demonstrated equal attention to detail and engineering finesse. It featured 5 8-inch operating tubes, carefully chosen for their balance of strength and lightweight properties. These tubes worked in conjunction with self-aligning ball bearing cranks, which minimized friction and wear while enhancing reliability. Multiple mass balance systems were integrated into the design, a critical innovation that helped stabilize the control surfaces during high-speed maneuvers. The linkage between the control stick and the elevator horns was established through a series of push-pull rod connections, ensuring a direct and responsive relationship between pilot inputs and elevator adjustments. A notable feature was the incorporation of mass balancing mechanisms throughout the control surfaces, helping maintain stability at high speeds. The hydraulic system integrated brake cylinders and control lines throughout the wings and fuselage. The rudder control mechanism mirrored the sophistication of the Focke-Wulf 190, incorporating wheel brake pedals as integral components of the rudder assembly. The fuel delivery system showcased advanced engineering with dual 238-gallon main tanks and a 53-gallon reserve tank. Each main tank featured 2 booster pumps, enabling fuel transfer between any tank and either engine. This system included a low fuel warning indicator that activated when fuel levels dropped below 250 liters. The cockpit interface incorporated several advanced features for the era. The aircraft featured armored front glass and an armored seat back for pilot protection. A distinctive aspect was the absence of an ejection seat. Pilots were instructed to either roll the aircraft or let its speed assist in emergency exits. The control interface became notably heavy at speeds exceeding 500 mph, particularly affecting aileron and elevator movements. Engineers developed solutions to address these high-speed control challenges, though reports suggest that some proposed modifications, such as an extendable control stick for increased leverage, never made it to production aircraft. The integration of multiple warning systems and gauges helped pilots manage the aircraft's complex systems. A particularly crucial addition was the fuel warning system, essential given the Me 262's significant fuel consumption rate, double that of contemporary twin-engine fighters. Weapons integration. The weapons integration of the Messerschmitt Me 262 showcased advanced armament engineering that matched its revolutionary propulsion and aerodynamic systems. The aircraft's firepower capabilities represented a significant advancement in aerial combat technology. The standard Me 262 A1, a featured 430mm Mk108 cannons mounted in the nose section, with the upper pair carrying 100 rounds each and the lower pair containing 80 rounds each. This configuration provided concentrated firepower without the convergence issues common to wing-mounted weapons. Over time, several specialized variants of the Me 262 emerged, each tailored to specific operational roles. The Me 262 A1, a U1 was outfitted with a mixed armament of two 20mm Mg151 cannons, two Ku-103 cannons, and two 30mm Mk108 cannons, creating a diverse and powerful weapons platform. The Me 262 A1, a U4 featured a single 50mm anti-tank gun, making it a specialized aircraft for engaging heavily armored ground targets. The Me 262 A1, a U5 variant, increased firepower even further by incorporating six Mk108 cannons, emphasizing sheer destructive capability. The Me 262 A2, a variant, was adapted for a dual-purpose role, combining two cannons with the ability to carry bombs, effectively transforming the aircraft into a fighter bomber. Each of these configurations demonstrated the adaptability of the Me 262's design, showcasing its ability to fulfill a wide range of mission profiles during its operational service. The Mk108 cannon system achieved a firing rate of 575 to 600 rounds per minute with a muzzle velocity of 1,570 feet per second. The operation of the cannon system relied on a sophisticated firing mechanism designed for efficiency and precision. Compressed air supplied from 8 bottles mounted within the aircraft's fuselage powered the system, providing the energy needed to cycle and fire the weapon. The pilot controlled the cannons through a contact stick switch, enabling simultaneous firing of all mounted guns for maximum destructive effect. To ensure optimal accuracy, the system was calibrated with a convergence setting designed for a 450-meter range. This configuration allowed the projectiles from the cannons to meet at a single point in space, maximizing their destructive potential at typical combat distances. For enhanced combat capability, engineers developed the R4M rocket system. The aircraft could carry up to 24 unguided R4M rockets with 12 mounted under each wing. These rockets proved highly effective against bomber formations, capable of destroying even the resilient B-17 Flying Fortress with just 1 or 2 hits. The ammunition feed system featured an innovative accessibility design. 235 1/4-inch access doors, piano hinge 1.5 inches off the top center line, allowed quick maintenance access through flush toggle latches. This design enabled rapid reloading and maintenance of both the gun mechanisms and ammunition drums. The entire nose section's attachment system demonstrated remarkable engineering efficiency. It connected to the mid-fuselage through 2 high-tension steel bolts at lower corners and 2 1/2-inch steel tubes at the upper section. This modular design allowed field crews to quickly replace damaged nose sections or reconfigure the aircraft for different mission requirements. The ammunition feed mechanism incorporated color-coded projectiles, light-tipped for high explosive rounds, and white-banded tips for armor-piercing ammunition. The weapons system proved highly effective in combat, with German pilots claiming 542 Allied aircraft shot down. However, the relatively low muzzle velocity required new combat tactics, as pilots needed to open fire at 500 meters and break off at 200 meters to avoid collision with their targets. Manufacturing innovations. Production challenges shaped every aspect of the Messerschmitt Me 262's manufacturing journey, as German industry struggled to mass-produce this advanced aircraft amid wartime constraints and Allied bombing campaigns. German engineers implemented a distributed manufacturing strategy, spreading production across multiple facilities operated by Messerschmitt, Heinkel, and Junkers. This approach included the innovative use of underground factories to shield production from Allied bombing raids. Each airframe required 6,400 man-hours to complete, with a base cost of 87,400 Reichsmarks per unit, excluding engines, armament, and electronics. The manufacturing network encompassed main assembly facilities at Messerschmitt plants, component production at distributed locations, underground facilities for critical components, and forest-based assembly lines for supplementary production. To expedite construction while conserving strategic materials, engineers implemented several optimization measures. Wing interiors were left unpainted in late-war production models, while assembly processes were streamlined to reduce material waste. The production system faced significant challenges, with only 107 aircraft delivered by August 1944. The efficiency and quality of manufacturing varied widely across the different types of production facilities utilized. Main assembly plants, which were staffed by skilled labor, generally maintained a standard level of production quality. These facilities were relatively well organized, but their output was limited by the availability of trained workers and strategic materials. In contrast, underground manufacturing facilities presented a mixed picture. These sites were often established in response to Allied bombing campaigns, which targeted traditional factories. While underground production offered some protection from air raids, the quality of output varied significantly. The workforce in these facilities was composed of a mix of skilled technicians and less experienced laborers, leading to inconsistent manufacturing standards. The most problematic production sites were the so-called forest factories, makeshift facilities hidden within wooded areas to evade detection. These factories relied heavily on forced labor, often under harsh and inhumane conditions. The reliance on untrained and undernourished workers contributed to a staggering rejection rate of 40% for parts and assemblies, severely undermining overall production efficiency. These discrepancies in production quality and efficiency across facilities reflected the immense strain on Germany's industrial base during the war. While engineers and planners worked tirelessly to innovate and adapt, the combination of resource shortages, labor issues, and logistical disruptions ultimately hindered the mass production of the Me 262, limiting its impact on the course of the conflict. Quality control presented significant challenges, particularly in the improvised forest factories. These facilities, sometimes constructed with wooden rails in open areas, struggled with quality standards, resulting in up to 40% of aircraft being deemed unacceptable. The quality control system for the Me 262's production incorporated a comprehensive set of measures to ensure reliability and consistency in manufacturing. Traceability protocols were established to track each component's origin, linking it to its specific production line, the shift during which it was made, and the individual responsible for its creation. This level of detail allowed for precise accountability and facilitated the identification and correction of potential issues within the manufacturing process. In addition to traceability, rigorous component inspection procedures were conducted at various stages of production. These inspections included verifying the quality of materials used and ensuring they met the required standards for strength and durability. Assembly precision was carefully checked to confirm that components were aligned and fitted with exacting accuracy. Structural integrity testing further validated the reliability of the final assemblies, ensuring that the aircraft could withstand the demanding conditions of flight. Despite these measures, production faced persistent challenges from material shortages, particularly in critical metals needed for engine components. The situation was further complicated by increasing Allied bombing raids, which disrupted supply chains and damaged production facilities. The manufacturing process required constant adaptation to changing circumstances. Many completed aircraft never reached operational units due to Germany's deteriorating transportation infrastructure. Those that did make it to service often faced operational limitations due to shortages of fuel, spare parts, and trained pilots. By the war's end, approximately 1,430 Mi-262s had been produced, though only a fraction saw active service. This number, while significant, fell far short of planned production targets, illustrating the immense challenges faced in manufacturing such an advanced aircraft under wartime conditions. Performance engineering. Technical performance data reveals the Me-262's exceptional capabilities as a combat aircraft. The jet fighter demonstrated remarkable speed and altitude performance that surpassed contemporary aircraft by significant margins. The Me-262's twin-jet configuration enabled a maximum speed of 540 mph, surpassing the P-51 Mustang by 120 mph at comparable altitudes. The performance of the Me-262 varied across different flight conditions, showcasing its versatility and adaptability to various operational scenarios. At cruising speed, the aircraft maintained an efficient pace of 445 mph, offering a balance between fuel economy and operational readiness. Near sea level, its maximum speed reached 511 mph, benefiting from the dense air to optimize thrust and performance. However, the Me-262 truly excelled at higher altitudes, where its twin jets achieved a peak velocity of 538, 19,685 feet. The aircraft's speed optimization relied on careful engine management, as rapid throttle adjustments could lead to performance complications. Engineers implemented specialized fuel supply regulators that maintained precise speed control above 6,000 RPM. The Me-262's altitude capabilities showcased impressive engineering achievements, including initial rate of climb 3,937 min, service ceiling 37,600 feet, time to 19,685 t 6.8 minutes. At high altitudes, the aircraft demonstrated unique performance characteristics. The turbojet engines experienced power reduction with increasing altitude, but this was partially offset by decreased drag in thinner air. Engineers designed the compressor stages to optimize high-altitude performance, though this created a delicate balance between power output and atmospheric conditions. The Me-262's combat performance characteristics reflected its advanced engineering. While not as maneuverable as contemporary piston-engine fighters at low speeds, it exhibited superior energy retention at high velocities. The aircraft's swept wing design and automatic leading edge slats increased lift by approximately 35% during tight turns. Combat tactics evolved to maximize the aircraft's performance envelope. Pilots developed specific attack patterns, including the high-speed slashing attack against bomber formations. The Me-262's superior speed allowed pilots to control engagement parameters, choosing when to attack and disengage based on tactical advantage. The aircraft demonstrated remarkable structural integrity during high-speed maneuvers. Test pilots successfully executed recovery from dives at speeds reaching 850 km/h while sustaining 8 loads. This structural strength, combined with the aircraft's speed advantage, enabled unique combat capabilities that conventional fighters couldn't match. Performance limitations primarily stemmed from engine characteristics rather than airframe design. The Jumo 004 engines required careful management, particularly during the acceleration and deceleration phases. Despite these constraints, the Me-262's performance envelope established new standards for fighter aircraft capabilities, influencing post-war jet fighter development significantly. Engineering limitations. Despite its groundbreaking capabilities, the Messerschmitt Me 262 faced significant technical limitations that impacted its operational effectiveness. These constraints stemmed from wartime material shortages, rushed development timelines, and technological immaturity. The Jumo 004 engine emerged as the Me 262's most critical weakness. These pioneering jet engines demonstrated remarkably short operational lives, requiring overhaul after just 10 to 25 hours of operation. Even with careful handling by experienced pilots, the engines rarely exceeded these limited lifespans, necessitating frequent maintenance cycles. Key reliability challenges included compressor stall and flame-out risks during rapid throttle movements, overheating issues due to insufficient airflow matching, turbine blade failures from thermal stress, and limited service life requiring constant maintenance. The engine's reliability issues stemmed primarily from material substitutions. The Jumo 004 B4, which entered large-scale production in October 1944, incorporated an air-cooled hollow blade wheel design that demonstrated a theoretical life of 150 hours. However, operational realities fell far short of this target. Material shortages had a profound impact on the development and production of the Me 262, forcing engineers to make difficult compromises in its design and construction. Germany's limited access to essential metal, chromium, cobalt, and molybdenum created significant challenges, particularly in the manufacturing of the aircraft's engines. The absence of sufficient nickel reduced engine durability, while chromium shortages limited heat resistance. Similarly, the lack of cobalt compromised the performance of turbine blades, and the scarcity of molybdenum raised concerns about structural integrity. The shortage of high-grade steel proved particularly problematic for engine manufacturing. Engineers had to redesign the 004 billion engine to minimize the use of strategic materials. This redesign, while enabling mass production, significantly reduced engine reliability and performance. The material shortages also influenced other aspects of the Me 262's design. When the engines turned out to be heavier than initially anticipated, the aircraft's layout had to be adjusted. Engineers relocated the engines from their original position in the wing roots to underwing pods, a modification that improved accessibility for maintenance and made engine replacements more efficient. However, this change also necessitated structural adaptations to the aircraft's wings, including modifications for better weight distribution, reinforcement of mounting points, and aerodynamic adjustments to maintain stability and flight performance. The project suffered additional delays due to Hermann Göring's decision to cut expenditures for jet engine research. This decision, combined with the prevailing belief that conventional aircraft could win the war, resulted in critical development time being lost. Operational limitations extended beyond technical issues. The widespread Allied bombing campaign severely disrupted production and supply chains. According to Major Wolfgang Schenk, maintenance became increasingly challenging due to parts shortages, forcing mechanics to manufacture replacement components locally. The engine's sensitivity to acceleration and power settings required careful handling. While later models incorporated automatic acceleration devices, the fundamental reliability issues persisted. The shortage of high-grade steel remained a constant challenge, particularly affecting the engine's high-temperature components. Manufacturing constraints also impacted quality control. The need to use substitute materials and rushed production schedules led to inconsistent build quality. Even when engines passed initial testing, their operational lifespan remained unpredictable, with some failing well before their expected service life. The aircraft's development timeline reflected these challenges. While the Me 262's first flight occurred in April 1941, engine development delays forced the use of a piston engine for initial testing. The first true jet-powered flight didn't take place until July 1942, representing a significant delay in the program's progression. These limitations had profound operational implications. Of the more than 1,400 Me 262s produced, only about 100 could be deployed simultaneously due to maintenance requirements and parts shortages. The constant need for engine replacement and maintenance created a significant logistical burden, limiting the aircraft's effective combat availability. The Messerschmitt Me 262 stands as a testament to German engineering prowess during World War II. This groundbreaking aircraft combined revolutionary jet propulsion, advanced aerodynamics, and sophisticated weapon systems to achieve unprecedented performance capabilities. Despite material shortages and technical limitations, particularly with engine reliability, the Me 262's design innovations influenced fighter aircraft development for decades. What fascinates you most about the Me 262's design? Do you think it truly outshines other iconic aircraft of its time, like the P-51 Mustang? Share your thoughts in the comments below. Thanks for watching.